First of all, I like to thank Alexei Miai for inviting me. So let us start with the basic questions. So look at this polynomial. So, so in this polynomial, if you look at the coefficients, so how many sign changes are there? So obviously there are 3 sign changes. Now if you multiply this, yeah. So there's 3 sign changes into 1. No, only 2. Okay, I want to write it actually that one. Sorry. So now if you look at this one, so there are potentially like there are actually infinite many coefficients. Now the question is how many sign changes are possible. So like answer is like it will be bounded by this actually, and we'll see this like in this talk how this is related to total positivity, and we'll see something more. So okay. So recall that yes, matrix A is totally positive of order k if all its minor of size at most k are positive. So in my definitions actually the totally positive is like minors are strictly positive actually. So and if all minors are for any square and for any matrix, if all minors are positive, then we call it totally positive actually. So basically it is true for any all k greater than equal to 1. So similarly, one can define totally non-negative matrices. So like the definition, like for the previous talk, this well, it was actually totally non-negative for matrix, and totally positive is all minors are positive. Okay, and we'll, so these matrices occur widely in diverse areas of mathematics and are listed here. So there is one more familiar class of positive matrices that is positive definite or definite matrices, and this definition is almost this is similar to somehow similar to positive semi-definite or definite matrices, but in this case the matrix need not be symmetric or square. And for the definition of totally for the definition of positive definite matrices, we need only principal minors, and here we are considering all minors. So first of all, I'll list some of the characterizations of positive definite matrices, which are which have analogous characterizations for totally positive matrices. So first one is like positive definite matrices are characterized by this their spectrum. So that is a matrix is positive definite if all eigenvalues are positive. And a similar characterizations was obtained by Grandmacher Crane in 1937, and they showed that a matrix is totally positive if and only if every square matrix of A has a positive eigenvalues. And moreover, that eigenvalues are also simple actually. And so they proved this result using, I think, Kronecker theorem for compound matrices and Theron's theorem for entry-wise non-negative matrices. So the there is this one is a Sylvester criteria. Yes, Sylvester criteria. So this instead of looking all leading principal all principal minors, so one can characterize positive definite matrices with leading principal minors. So like again, this question is whether instead of all minors can you reduce this number of minors, and this was done by faculty in 1912 for totally positive matrices, and that is further refined by Schoenberg in 1955 for totally positive matrices of order k. So this is totally positive of order k if all contiguous minors of A of size at most have positive determinant. So here the contiguous definition means that rows and columns are indexed by consecutively. So the converse is obvious. So this now this is totally positive if all contiguous minors of size at most have a positive determinant. And okay, so another one is like this class of totally class of positive definite matrices are dense in positive semi-definite matrices. And this proof is very simple using this one can show that. But that is quite non-trivial for uh, totally positive matrices. So, so that was a result by Whitney in 1951, and she showed that the set of, if we take any uh, totally non-negative matrices of order k, that can be approximated by a sequence of totally positive matrices of order. So in this statement, if you start with a symmetric totally non-negative matrices of order k, so that can be also approximated by a symmetric totally positive matrices of order k. And okay, so next is the set of positive semi-definite matrices that is closed under entry-wise limits, and similar results also holds for totally non-negative. So because I mentioned so many characterizations that have like similar results, so just I like to mention one about that, which is satisfies by totally non-negative matrices, but not very positive. So if you take any two positive semi-definite matrices, then that is not closed under multiplications. But if you take any two totally non-negative matrices or totally positive matrices, that is closed uh, under multiplication, and that is just basically nothing but a Cauchy. Okay. So these are the some basic results. So now let us look at some examples of. So our first example is generalized Benderman matrix. So if you take any sequence of non-positive real numbers, x1, x2, xn, and any real, and again any sequence of any real numbers alpha and alpha n, then this m by n matrix, that is totally positive. And the proof of this one is basically again uses the Descartes rule of signs. Okay. And our next example is Gaussian kernel that we I think I discussed yesterday again and again. So that is nothing. So if you take any positive sigma and in sequence of strictly increasing sequence of real numbers x1 to xn and y and y, then this Gaussian kernel defined by this is totally positive. And so like if you take any square submatrix of this matrix, that is again exactly of this form, and if we factorize it, we'll get in this structure. So here the second matrix is nothing but generalized Benderman matrix. So all the minors are positive. And yes, also for the next example is Topli's cosine matrix. So if theta belongs to this interval, one can verify that all 1 by 1 and 2 by 2 minors are non-negative, and the rank of this matrix is 2. So any 3 by 3 and higher order minors are beneficials actually. So that will be a totally non-negative. And our next example is an historical one, which comes from the theory of one-sided Fourier frequency sequence. So let us first look at such sequence in general. So a real sequence is called one-sided Fourier frequency sequence is the following semi-infinite Topli's matrices totally. So in other words, if you take any finite square matrix, then its determinant is non-negative, and it is encoded by the corresponding generating function. So here is an example of one-sided PF sequence. So if you take any square submatrix of this matrix, then it is either a matrix with row zeros or column zero, or it is a upper triangular matrix with diagonal entries alpha, or a lower triangular matrix with diagonal entries 1. So in all these cases, we get a non-negative determinant. So this will give an example of one-sided PF sequence. And so, and another way of constructing one-sided such sequences is follows. So take two one-sided PF sequence, then you will get two totally non-negative semi-infinite Topli's matrix, and we know that the product of two Topli's matrices is again a Topli's matrix, and also the product of two totally non-negative matrices is again a totally non-negative. So this will and the product of two and lower triangular matrix will be again a lower triangular. So basically, this will give a this is a semi-infinite again a semi-infinite Topliss matrix. And so and their generating their corresponding generating functions also satisfy this property. So basically, psi of ax is times psi of bx, nothing but now combining all these facts on this say that the every real sequence L with these generating functions give a finite one-sided PF sequence, and their corresponding Topliss matrices totally. Now the question is whether there exists any other finite one-sided PF sequence. And remarkably, there are no others. And this was a result by Schoenberg in 1955. So now let us come to our historical example. So if we take n not equal to 1, and if we set alpha 1, alpha 2, alpha n by gamma by n in the above example, we'll get a finite one-sided PF sequence. And we know that the set of all totally non-negative matrices flows under entropy limits. So the same thing holds for one-sided PF sequence, and their coefficients of their corresponding generating functions also. So if you take limit of this function, we'll get an infinite one-sided PF sequence, and their corresponding Topliss matrices are totally. And this was proved by Fekete much before their Schoenberg result. So next I'll talk about a fundamental property that was the title of this talk actually. So variation diminution property, and totally non-negative matrices satisfy this property. So before we proceed, let us look at a simple definition. So for a non-zero vector x, so s minus of x denote the number of sign changes after deleting the all zero entries. Okay. So for any vector, you can denote all the zero entries and whatever the number of sign changes, that will be denoted by s minus of x. And we set s minus of 0 equal to. So the variation diminishing property means if a matrix acts on a vector, the number of sign changes goes down. In other words, so s minus of ax will be less than equal to x. And the phrase variation diminution was coined by Fourier. And this was in use since Descartes' rule of signs in 1600s, and Laguerre made several versions of variants of rule of sign. So here is a particular example. So given a polynomial f of x and non-negative real number gamma, the number of variation in this function is non-increasing, and in fact it is bounded by the value gamma equal to 0, and which is nothing but f of x. And since f of x is a polynomial, the number of variation is finite. So what Laguerre result actually says, so for any real polynomial and then any positive gamma, so e to the power gamma x times f of x, this function has a this is a infinite series, and there are infinitely many coefficients. So potentially there are infinitely many sign changes. But this result says that there are only finitely many sign changes. So that was that example actually basically. So here, this is number of sign changes in this coefficient of this function is basically at most actually 2. So Laguerre did not prove this result completely. Fekete, in correspondence with Fourier in 1912, reformulated this problem in terms of total positivity, and they proved the following. So if we take this semi-infinite Topliss matrix, then for any finite vector C, s minus of T of C is less than equal to s minus of C. Okay, it satisfies variation diminishing property for a finite vector. So now, so now for this now specialize this T of A for a T gamma, for where gamma is we coming from this Fekete example. And if we take any polynomial, okay, and construct a vector using the coefficient of this, then the variation of this function is nothing but the number of sign changes in this vector actually. And by this result, that is less than equal to the number of sign changes in this vector C. What is this? Is nothing but the variation of this polynomial. So basically, our historical journey goes from the Descartes' rule of science in 1600s to refinement by Polya in 1880s. Then Fekete correspondence between Fekete Polya in 1912. Then Schoenberg came to the picture, and he showed that if we take any MIN totally non-negative matrix, then this satisfies the variation dimension. Unlike the Fekete case where we are considering only triangular matrices. So now, if you look at this statement actually, so this statement also holds for if we replace A with minus of A. Okay. And if A is a totally non-negative, so if you look at minus of A, then it's all 1 by 1 minus will be less than equal to 0. 2 by 2 will be greater than equal to 0. And 3 by 3 again less. So it is, so signs are changing actually. So now the question is, can we characterize the matrices which satisfies this property? And in 1936, Morskin in his PhD thesis able to answer this question. And so before we proceed, let us look at some more definitions. So here is a definition. So a matrix A is called strictly sign regular if there exists a sequence of signs epsilon k such that every k by k minor have an identical sign epsilon. So for example, for all 1 by 1 minor have a one particular sign, for all 2 by 2 minor have a sign that need not be like positive. Then that matrix is called strictly sign regular. So for example, if all the signs are positive, then we call it as a totally positive matrix. And if minors are also allowed to vanish, that is basically if signs are non-strict and if that is minors are also allowed to vanish, then we call it a sign regular matrices. So that for a particular case it will be. And Morskin in his PhD thesis showed that if A is a m by n matrix which rank n, then A satisfies some A is strictly A is sign regular if and only if A satisfies the variation division. Okay, so he needs this additional condition, this rank of A. So Morskin in his PhD thesis also studied this Morskin, the famous Morskin transposition theorem, Fourier Morskin elimination algorithm, and other things also. So, okay, so this Morskin in his thesis, he is able to characterize with these additional conditions. And in this, if you look at this statement, it doesn't say anything about the sign pattern of this matrix. It just says that it is a SR matrix. We don't know anything what is the sign pattern of it. So then Grandmacher Crane in 1950 made further fundamental contributions to variation diminishing property. So they are able to characterize totally non-negative matrices using variation diminishing property, and they are with some additional conditions, but also they remove the condition of rank. Okay. So in particular in Morskin results, we don't know about the what is the sign pattern, but now we can know that what is the sign pattern actually. So here is which was later defined by Brown, Johnson, McGibbon. So I'm looking at this simpler version of this. So A is totally non-negative if it satisfies the variation diminishing property, and if moreover equality occurs here, then it satisfies some additional conditions. And this additional condition is the first non-zero component of X has the same sign as the first non-zero component of X. Okay. So they are able to so in a sense, they are able to first of all they improve the Morskin result. So because they remove the rank conditions, and also they able to identify the particular sign. Now the question is, now can we characterize totally positive matrices or strictly signed regular matrices using variation? So to do this, actually, Grandmacher Crane introduced a new way of counting the number of sign changes, and so that is what. So let me explain this with an example. Actually. So if you look at this, actually, s minus of 0, this vector actually. So how many sign changes are there? This is only 2. But now if we replace 0 with minus 1 and this one with like anything, positive, negative, that will not affect anything. So then what will get, the number of sign changes will increase actually. So if you replace, for example, so in this vector, so here according to our previous count, the number of sign changes is only 2. So now if you replace 0 with minus 1, then how many sign changes will be possible? That will be 4 actually. Okay. So now if you replace here anything with plus 1 or minus 1, that will not affect anything actually. But if you replace here instead of minus 1, 1, then again it will not affect it. Number of sign changes will be the same. Okay. So what Grandmacher Crane did, they look at the, so what they did, they replace actually this 0 entries with either plus 1 and minus 1, and then look at the maximum number of sign changes in this sequence actually. So basically you can replace whatever 0 entries with your choice, plus and minus 1, and then look at the maximum sign changes. So in this case it will be 4. So that one they denoted by s plus of x actually. Okay. And okay. So for example, like obviously this s minus of 0 will be less than equal to s plus of x. And we set s plus of 0 equal to n.
And minus 1.
That is, but we are assuming that it is n actually. Of this, it is defined for non-zero vector. For 0, this
no, for vector of length n.
Yeah. So this definition is
the number of sign changes.
Yeah. So this definition is for a non-zero vector actually. So if it is all the entries are 0, then we are setting this actually. Yes,
but you can't put signs such that.
Yeah, that way you can do it, but that is the convention. So this definition is like s plus or s minus, that is for a non-zero vector. If it is all the 0, all the entries are 0, then we are setting s minus 0 is 0, or s plus 0 is 0. I hope the definition is clear. Oh. So using this, the new OS sign count. So Grandfather Crane again in 1950, they are able to characterize totally positive matrices, which was again later refined by Brown, Johnson, McGill. So here, what is the result? So A is totally positive if and only if it satisfies the variation diminution property with this new sign. So we are, so if I say like for a totally positive or strictly signed regular, the variation diminution means we are looking at this sign changes actually the left hand side. So that is s plus of x will be less than equal to s minus. And then this additional conditions, if this is equal, then instead of first non-zero component, we look at the first component. If the first component is a non-zero, then we'll just look at what is the sign of this component. If 0, then the entries what will put plus 1 or minus 1 to compute this s plus of x, we look at that sign actually. So this must be equal to the must be same as the first non-zero component of x. So using this, they are able to characterize this totally positive matrices. So in this same book, actually, they also characterize strictly signed regular matrices, but with an additional condition. So in they showed that for a m by n matrix with m strictly greater than n, then A is strictly signed regular if and only if it satisfies this condition. So for a totally positive matrices, they're able to remove these conditions, and we need they added some additional conditions to characterize it. But for a general SSR matrix, they need this extra condition. Okay. Also, in this result, they did not mention about what is the sign pattern of this SSR matrix. So they only for a one particular sign pattern they are able to identify it, but for a general SSR, they can't say it. So this leads us to the following questions. So can we remove the restrictions imposed by Grandmacher-Crane here, or Motzkin, that is the rank hypothesis, to the rank of matrix must be n actually. Okay. And this, so Grandmacher-Crane, they are able to characterize totally positive and totally non-negative matrices. So basically that is a particular sign pattern, all signs are one. So can we characterize SR or SSR matrices or other sequence of sign patterns using the. So in this talk, we'll see that we are able to answer these questions with recent work with Chilang Yadav. So the first one is, suppose you take any rectangular matrix A, then if A satisfies this condition, then A is SSR. And this is again. Okay. So we are able to remove the size hypothesis constraints that provided by Grandmacher-Crane. Now, again, so in this result, again, we don't know about the what is the sign pattern of this matrix. We are only ensuring that A is SSR. We don't know what the sign pattern. So, and so basically, so again, the question is now, like for a totally, if you remember the statement of totally positive matrices, what we did with this Grandmacher-Crane did, they included some additional hypothesis, and using this, they identified the sign pattern of the matrix actually, that all the signs are. So in this, again, in this statement, whether we can add something more constraint and identify the sign pattern of this matrix. So answer is yes, and here is our result. So suppose you start with any and the sign pattern, like, according to your choice, then A is SSR of this particular sign pattern. You can only, first of all, it satisfies this condition, that is variation diminution with S plus of A. And if this equality occurs, then it satisfies this addition of I. So if A is SSR epsilon, so this condition is basically natural, because if A is SSR epsilon, then it also satisfies, it is true for this. And also if a matrix satisfies this condition, then you can say. Now, if you look at the this second statement, or all other statements of variation, right? This the set of test vector is uncountable set. Because this statement is true for all x. So now the question is, can we reduce it to a countable one, or even better, a finite set actually? And so we are also able to do this, and to this, I think I already defined contiguous submatrix definition. So these two statements are further equivalent to the following one. So it is enough to check at the variation diminishing property for a particular vector for each contiguous submatrix. So the vector is constructed as follows: take any vector from alternating biorthen and look at the adjuvate AK times. If variation diminishing property holds for that vector, then the matrix is a strictly signable. So basically, the idea is for each square submatrix, for each contiguous square submatrix, you have to look at one particular vector from alternating biorthen, and for that particular biorthen, if the variation diminishing property holds, then the matrix is SSR of the particular sign pattern. Okay. So now, if you look at this, the way this vector is constructed, which is we are taking this vector from alternating biorthen. So now the question is, can you take vectors from any other biorthen and characterize this strictly signable matrix of particular sign pattern? And answer is no. And in fact, we prove something more. So, the result is that if we take any vector, okay, which is all the coordinates are non-zero, and at least two successive coordinates have the same sign. So basically, we are avoiding the alternating line. Okay. And if your matrix A is strictly sign regular of order n minus 1, we are looking at a square matrix, and if it is a strictly sign regular matrix of order n minus 1, okay, then also it satisfies the variation diminution for that particular. So that is S plus of x naught is that. And so, like to say that this we cannot characterize strictly sign regular matrices from other biorthens. So we need to construct a matrix which is strictly sign regular of order n minus 1, but it is not a strictly sign regular. So basically, in particular, we have to show that determinant is 0. Because if it is a determinant is positive, negative, then that will be some particular class of strictly sign. So we did this actually. So we are able to do this actually, and this follows from again using the Gaussian kernel. So take any totally strictly sign regular matrices of size n minus 1, and by a classical result of Grandmacher grains, such a matrix always exists actually. Now what we can do, we can embed this matrix inside a bigger matrix by adding a zeros actually. So that will be what? That will be strictly sign regular matrix. Okay. And what rank of this matrix will be n minus 1. Now what we can do, we can pre and post multiply by this Gaussian kernel. Okay. So we'll, by using Cauchy-Binet formula, we'll get a strictly sign regular matrix of order n minus 1. But the determinant of this matrix is 0 actually. So we are able to prove that if we take any vectors from any other orthant apart from the alternating biorthant, then it satisfies, and if the matrix is a strictly sign regular of order n minus 1, then it satisfies variation diminution. And there is an example of at least existence of strictly sign regular matrix of order n minus 1, which is not SSRN. So that will give that we cannot characterize strictly sign regular matrices from test vectors of any other biorthant apart from alternating. So in that sense, actually, this is the best possible way we can. Okay. So as a particular case of this result, we are able to obtain some of the results that we proved in 2022. So we in that paper we are able to characterize on characterize totally positive matrices using variation diminishing property. Okay. Which basically we are able to provide a single vector test that we discussed actually earlier for a totally positive matrices also with test vectors of alternating biorthant. Okay. And also we in that paper also we apart from other things we showed that so these test vectors if we take these test vectors from any other biorthant apart from this alternating biorthant, we cannot characterize total positive matrices using derivation. And so in that paper also we need to construct a matrix which is TPn minus 1 but not TPn. So to do this actually we basically used a Fourier frequency function of Carlin, and so here is this actually. So if you look at this Fourier frequency function, so Carlin showed that if alpha belongs to this set, then this is totally non-negative order. Okay. And recently Apurva showed that if we take any sequence of positive any sequence of real numbers y1 to yk which is strictly less than x1 x2 xk, then this matrix will be totally positive of order k if alpha greater than equal to k minus 2. And it is not totally non-negative of order k if alpha below 2. Okay. Now what we can do, so suppose we take any n which is greater than equal to 3 and alpha lies in this interval. Okay. So what we can say that from the previous result, because alpha is greater than equal to n minus 3, okay, so that means what? This is totally positive of order n minus 1. But alpha is less than equal to n minus 2. So that means what? This is not totally non-negative of order n. That means what? This determinant must be less than 0. Okay. So this examples gives us an totally positive matrix of order n minus 1 with determinant which is also not a totally positive matrix of order n. So in that particular paper, we are able to provide a we have probably exact example of this instead of just a existence of an example of a totally positive or matrix, which is that particular. Okay. So like if you are so if you look at this what is Motzkin. So if you look at this Motzkin result, okay, so basically we are able to completely characterize strictly signed regular matrices of any given sign pattern actually using variation diminution property. Now this the question is this Motzkin characterizations. So Motzkin is able to characterize this signed regular matrices. The question is now pending for signed regular matrices. So Motzkin is able to characterize signed regular matrices using variation diminution property, but with this additional hypothesis. And later Grandmacher Crane able to they are able to characterize only totally non-negative matrices, that is a particular sign pattern for a complete. Now the question is, can you also characterize signed regular matrices or other sign pattern? And so that is a question. So now the question is, so this similar to the strictly signed regular matrices, can you characterize signed regular matrices for other sequence of sign patterns? And the next question is, can we strengthen this result using a single test paper? And answer is yes for both of these questions. In the same paper, actually, we are able to answer this question. That is, if you take any sign regular matrices of any particular sign pattern, that can be characterized. Okay. So now, so in the as we know that also in the beginning of my talk, we mentioned that this totally positive matrices have lots of applications in different fields of branches of mathematics. And I believe this these applications are possible because of their huge collections of examples. Actually, so one can play with these examples and do many things. Actually. And now this, when we talk about the strictly signed regular or signed regular matrices, this is like there's no such like huge collection of examples. Only a classical results of Grandmacher Crane in 1950 assured us that for any particular sign pattern of any size, the strictly signed regular matrices exist actually. Now the question is, can we construct actually explicitly signed regular matrices for any particular sign pattern or any given given size? And so basically in our new work, actually, we are able to answer these questions. And the answer is basically we have developed an algorithm actually to construct explicitly any size regular matrices of any given size and sign pattern. And this algorithm is basically depends on the fact that so if we take any SSR matrix, okay, so you can add a new column at the beginning or at the end of this matrix. The resulting matrix will be again a SSR matrix. Similarly, you can add a row or at the top or at the bottom of this matrix, so that the resulting matrix will be again a SSR. So now the question is, suppose if I suppose you take any 4x2 SSR matrix. So what will be this? There will be 4 rows and only 2 columns. Now, if we add another row, another column, okay. So that means what? Minor of new sizes also occur here, 3x3 actually. So we are able to show that actually, whatever sign you want for the 3x3 minors, we can add such column in such a way that all the 3x3 minors of that particular sign. So if you want it is a positive, then we can add a column so that it will be. These are all the signs of the smaller order, and the new order what will be there, that will be of that particular sign. So within this, basically we are able to develop an algorithm. Okay. So basically you can start with one particular entry, and you can algorithmically you can construct of any SSR matrix so far. So basically the new sign that order of the larger minus basically depends on us. So that will give a so basically that is the result actually. So we can add a line at any border, such a border means either on top, bottom, or left and right actually we can column, so that the resulting matrix is again a SSR, and if new minor of larger size occur, then that can be either positive or whatever. Now, so this leads us to the question actually. So we are saying that we can add columns here and here actually. The question is whether we can add column between any two columns actually, or any row between any two rows. So okay, so we are also able to do this actually. So if we, so here line means either row and column. So if we take any sign regular matrix of any size, so a line can be inserted between any two consecutive column or consecutive rows. Again, if this after inserting a line, actually if the new larger minors occurs, that can be your according to your choice actually. Whatever sign you want, that according to this we can insert the line. So yeah. So yeah, that is what actually, and this this I think we can finish it within a week actually. So in this paper actually, that is the tentative title of this paper. So where we can like we are able to construct a sign regular matrices, strictly sign regular matrices for any size. So for a constructing is sign regular matrix is quite easy. It's like if you take any sign regular, you can put row of 0 or column of 0, that will give you a higher order size. But for second strictly sign regular, that we need a clean line. So I hope like so this after this actually basically one can construct strictly signed regular matrices of any order, any size. So one can play with this and there will be lots of more applications after this.
Very interesting thought. Questions?
As you mentioned, totally non-negative matrices are closed with respect to the usual product.
Yes.
But if we consider Hadamard product, element line, it is not the case. But there is an interesting class introduced, the class of totally non-negative matrices introduced by Charlie Johnson, called Hadamard core or something. So you consider those matrices where Hadamard product is satisfying this role. So when the Hadamard product of two totally non-negative matrices is again totally non-negative. And there are many open problems describing this class. It could be interesting to apply the technique we're doing to characterize this class.
Yeah.
I'm sure something could be done in better.
Yeah. So So like one thing, like basically we are doing actually basically so it's not like a Hadamard product in the sense that like we are looking at the entry-wise power of entry-wise power which preserve the strictly sign regularity actually, or sign regularity, and we are it's almost done actually. We are able to characterize all functions which preserve that actually strictly sign regularity or sign regularity actually. Either it is for whole class or a particular sign pattern. So that is actually like that we need to. So that is like not exactly your answer, but yeah.
Characterizing maps is one thing,
Yeah.
but characterizing this subclass is a different thing, but also interesting. But both are interesting.
Yes, please.
Some questions. One is this line insertion is done in Charlie's and completion problems in TPK.
Yes.
I don't know if you're using similar methods or not.
So because you can't, you can think about it something similarity, but you can't think exactly similar because the Charlie, this idea is basically that is totally positive. So totally positive, your life is quite easy.
Yeah.
So if you want to add line at the start or bottom, actually, then you can take the value at large as possible actually, and do it actually. But if you want to look at the strictly sign regular matrices, so because it's changing sign actually, suppose anything can be possible, no?
Yeah.
So it will be more difficult actually. You can put a like, suppose I want to say that suppose if you want to start with a totally positive matrix of 2 by 2, you want to make it a like, suppose it's a two column, okay, you want to another 8 column. So what we can do, you can choose here something, then you can put as large as possible so that it will be then you can put as large as possible that. But for a strictly sign regular, you don't know, like you can't do that actually. So that problem is like quite difficult from like different and difficult in that sense actually.
That's exactly what I was asking. The techniques are like.
Technique is quite different from that actually.
Can I ask another question? Can I ask another question? So if your matrix is TPK and not TPK plus 1, then you say anything like the number of changes in the sign or something like that?
So so basically yes, so we can say that like number of sign changes of the vector. So we can know that like if it is a TPK, then it satisfies this variation diminution for a vector which has like so you are starting with a k plus 1 I believe like a matrix actually. So basically, for example, you start with any size actually. So basically, then you have to look at the vector which has size number of sign changes is only k minus 1 actually. Up to that we can use. So basically, that will be again follow from this the result that we said that this is TPN minus 1 or SSR n minus 1.
Yeah.
So that it should be. After that, it is not really.
After that, what?
After that, it may be for some particular one, it may be satisfied. Yeah, no.
Okay. Thank you.
More questions? Yes, please.
Well, my understanding there's an analogous concept not for matrices but for kernels, right?
Yes.
And okay, there's also the notion of sign changes for functions.
Yeah.
But for functions, I personally am more interested in zeros, and there's a subtle difference between counting zeros and counting sign changes. And
I think he's talking next actually. This actually about this actually exactly.
Because Grunberg has this trick to move between these two, and I was never comfortable with that.
Yeah.
So I'll keep asking afterwards.
Okay, fine.
Exactly like.
No, but as you know, integrating against a Polia frequency kernel, the topless kernel, Also, it does not increase the number of non-real zeros, right?
Yeah,
That's the-
right, and he. Argument.
And then he applied it to polynomials rather than functions.
Right.
And then that's how he got to,
Okay, so I'm.
we will.
keep watching it.
I don't know.
That's why we shifted our talk actually, so that I can give you for a matrix and we can start with.
Yeah, we switched it so
Okay.
that I'll talk after him.
Questions? One comment, the book is translated, is available in American
Yes.
Society Translation.
Yes.
So don't be frightened by the Russian.
Okay.
Thank you so much for it.